Today's lesson is all about arithmetic with signed numbers. I'm going to begin by talking about addition of signed numbers. Candace is going to follow me. She's going to talk about subtraction of signed numbers. And Anne is going to finish up by talking about multiplication and division of signed numbers. Now, in my development of addition of signed numbers, I'm going to begin by talking about what I call the counting principle. I'm going to extend the counting principle to a model that uses what we call signed chips. I'm going to talk about some rules that you just plain have to memorize. Then I'm going to move to a number line model of addition of signed numbers. And I'm going to immediately be followed by Candace extending this to subtraction of signed numbers. So you're probably wondering, what do I mean by the counting principle? I'm talking about the way you learned how to add when you first learned about addition. And when you first learned about addition, you were limited to objects that you could count. For example, let's consider 4 plus 5. Let's think of something we could count. We could count chickens, after they hatch, of course. Let's start with 4 chickens. We want to add to this 5 chickens. If we count our chickens, we can see that altogether we have 9 chickens. So what we write on our paper is 4 plus 5 equals 9. Now it turns out that you can take this counting idea and actually apply it to negative integers as well as positive integers. But in order to do that, we're going to need a model that's a little more sophisticated than a chicken. So our next order of business is to show the chickens the door. So now let's talk about using signed chips for our counting instead of chickens for our counting. What I have here is a little model that I'm going to use that's going to allow me to add not only positive integers, but negative integers as well. You can see that there's 3 parts to the screen. There's the counting area. That's where I'm actually going to keep track of my sum. There's a bank. If I wasn't doing this on a computer, I'd have a stack of chips. I'd have a stack of positive chips, negative chips, and 0 chips. And I keep those in what I like to call the bank. And then I have this area down here where I'm actually going to write the result of the addition, what you would write on your paper. The chip model is simply to help you understand. It's not work that you would show when you were working the problem. That's why I've got this clearly identified solution area, so you clearly see what you would write when you were presented with a problem. So what I'm going to do with these signed chips is I'm going to use them to represent both positive numbers and negative numbers. For example, if I wanted to represent positive 2, I would use 2 positive chips. If I wanted to represent negative 3, I would use 3 negative chips. Now you might be wondering, what's the purpose of the 0 chip? The 0 chip is kind of the magic chip, because every time I encounter one positive chip paired with one negative chip, I can replace those 2 chips with a 0 chip. It's kind of like voting on a yes or no question. One yes vote and one no vote taken together nullify one another. It's almost a no vote. So right now, if I was modeling 2 plus negative 3, I could replace this pair of positive and negative chips with the 0 chip, and this pair of positive and negative chips with the 0 chip. And we all know that adding 0 doesn't change the result on the sum, so I could take these 2 0 chips and move them right back to the bank. Let's see some specific examples. Let's evaluate 4 plus 5. Let's use our chips. Let's leave the chickens behind. Here's 4 positive chips in my counting area. Now I need to add to that 5 positive chips. Altogether, I have 9 positive chips. 9 positive chips represent the number positive 9. So on our paper, all we would write is 4 plus 5 equals 9. Well, what if we were asked to evaluate negative 4 plus negative 5? This is almost exactly the same problem we just worked. The only difference is we're going to start with 4 negative chips, and then we are going to add 5 additional negative chips. So altogether we have 9 negative chips. 9 negative chips represents the number -9. So in our solution, what we would actually write on our paper is that -4 plus -5 equals -9. Let's start mixing up the chips. So we have our first rule for addition of 2 signed numbers. If the 2 numbers share the same sign, then the sign on the sum is the same as the sign on each number in the sum. When we added 2 positive numbers, we got a positive number. When we added 2 negative numbers, we got a negative number. The absolute value of the sum is equal to the sum of the absolute values of the numbers in the sum. Boy, that's a mouthful. In both cases, we were adding together 2 numbers that had absolute values of 4 and 5. And in both cases, the absolute value of the sum turned out to be 9. The difference is that when we added 2 positive numbers, the result was +9, and when we added 2 negative numbers, the result was -9. Now, as I just mentioned, this phrase absolute value is kind of a mouthful. Sometimes people like to use the word magnitude rather than the phrase absolute value. And if you prefer that, that's great. Just remember that the magnitude of the sum is equal to the sum of the magnitudes of the numbers in the sum. Now let's see what happens when we start mixing up the signs in the sum. Let's evaluate 7 plus -3. I need to begin by moving 7 positive chips into my counting area. I need to add to that, see the plus sign, 3 negative chips. Now I get to use my magic 0 chip. Every pair of positive and negative chips nullify one another. For example, here's 1 positive chip, 1 negative chip. We can think of this in a sense as 1 step forward, 1 step back. The net result is 0 steps in a sense. So I can replace this pair with a 0 chip. There's 2 more pairs of positive and negative chips. Each one of these pairs can be replaced with a 0 chip. Adding 0 does not affect the sum. So I can take these 0 chips and move them right back into the bank. And I'm left with 4 positive chips. What does this tell me? It tells me that if I take 7 and I add -3, the result is +4. You might be thinking, well, that's kind of just like subtracting 3 from 7. Well, in a sense, I did. Let's go back. At first, I had 7 positive chips. What happened to 3 of those positive chips? They turned into 0 chips with the help of some negative chips, and they were taken away. Let's evaluate -5 plus 8. We start with 5 negative chips. We need to add to this 8 positive chips. Let's identify pairs of positive and negative chips. Each pair can be traded in for a 0 chip. Adding 0 won't change our sum, so we're left with 3 positive chips. What do we write? We write that -5 plus 8 equals +3. What if we started with +5 and then added -8? Let's look for our pairs of positive and negative chips. Each pair can be swapped with the 0 chip. Adding 0 doesn't change the sum, so the zeros are out of there, and we're left with 3 negative chips. What do we write? We write 5 plus -8 equals -3. Let's consider those last 2 examples. What was similar? What was different? Well, in both cases, the absolute value of the sum ended up as +3. When the negative number had the larger absolute value, that would be -8, has an absolute value of 8, which is greater than 5, look what happened in the sum. The sum turned out to be negative. When the positive number had the larger absolute value, 8 as opposed to the absolute value of negative 5, which is 5, look what happened. The sum turned out to be positive. So in both cases, the absolute value of the sum ended up being the positive difference between the absolute values of the two numbers in the sum. When the negative number in the sum had the larger magnitude, the larger absolute value, the sum came out negative. When the positive number had the larger magnitude between the two numbers in the sum came out positive. Let's put that in words. Here's the rules you just need to memorize. If the two numbers have opposite signs, then the sign on the sum is the same as the sign on the number with the larger absolute value. The absolute value of the sum is equal to the positive difference between the absolute values of the numbers in the sum. Again, if you prefer the word magnitude, you could think of it this way. If the two numbers have opposite signs, then the sign on the sum is the same as the sign on the number with the larger magnitude. And the magnitude of the sum is equal to the positive difference between the magnitudes of the numbers in the sum. Now there's one case we haven't considered yet. What if the two numbers have opposite signs but equal absolute value? In this case, the sum is 0. For example, if we took 3 and we added negative 3, the result would be 0. 3 positive chips, 3 negative chips, 3 pairs of positive and negative give us 3 zeros. 3 zeros is just a whole lot of 0. Two numbers that add to 0 are called additive inverses because their sum is what we call the additive identity. Here's a place where you're going to have to make a conscious effort to really memorize something. Additive inverses are two numbers that add to 0. 0 is frequently referred to as the additive identity. It's really important that you memorize these two phrases because when you hear these phrases coming out of our mouths, or when you read these phrases in the textbook, you want to be able to understand what we're trying to communicate. That's why you need to memorize the meaning. We saw earlier our other rules, that if two numbers share the same sign, then the sign on the sum is the same as the sign on each number in the sum. And the absolute value of the sum is equal to the sum of the absolute values of the numbers in the sum. Let's put this to action. Let's compute several sums. In my first example, I'm being asked to evaluate negative 3 plus negative 18. The two numbers have the same sign. They're both negative. So the first thing I observe is that the sum is negative. Then I need to figure out what's the magnitude of the sum. I take the magnitudes of the two numbers and add them up. 3 and 18, that's 21. So the magnitude of the sum is 21. Negative 3 plus negative 18 equals negative 21. In my next example, I'm being asked to evaluate 15 plus 17. Now you might be thinking, I don't need no rules to add 15 and 17. You're right, at least I hope you're right, but I want you to show that the rules do apply nonetheless. 15 and 17 are both positive. When the two numbers have the same sign, the sign on the sum is the same as the sign on the numbers in the sum. So the sum of two positive numbers is positive. The absolute values of these numbers are 15 and 17. When I add 15 and 17, I get 32. So what is the positive number that has an absolute value of 32? I think it's 32. The rules work even when both numbers are positive. Next example, negative 92 plus 12. These two numbers have opposite signs. So the first rule I need to consider is that when the two numbers have opposite signs, The number with the larger absolute value determines the sign on the sum. 92 is larger than 12. 92 is the absolute value of the negative number, so the sum is negative. What's the absolute value of the sum? It's the positive difference between the absolute values of the two numbers in the sum. 92 minus 12 is 80, so the absolute value of this sum is 80. The sum is negative, its absolute value is 80. That's the number negative 80. 100 plus negative 94. The numbers have opposite sign. So the first thing I need to consider is which of the two numbers has the larger magnitude. It's 100. That's the positive number. So the sign on the sum is going to be positive. What's the absolute value of the sum? It's the positive difference between the magnitudes of the two numbers in the sum. 194. What's the positive difference? It's 6. So 100 plus negative 94 is positive 6. In our next example, we're back to an example where the two numbers have the same sign. Both numbers are negative. When the two numbers have the same sign, that's the sign on the sum. So the sign on the sum is negative. Add the absolute values of the two numbers, 27 and 44, and we get 71. So the absolute value of the sum is 71. Hence, negative 27 plus negative 44 equals negative 71. One last example. 39 plus negative 39. These numbers have opposite signs, but equal absolute value. And in that case, the numbers add to 0. Here's a little vocabulary review. When you have two numbers that add to 0, they're called additive inverses. And we call 0 the additive identity. Why do we call it the additive identity? Because it doesn't change the identity of a number when you add it. 7, add 0, 7's feeling good, it's still 7. It doesn't affect the identity of 7 when you add 0. Now I'm going to show you one more model of ways that you can think about adding signed numbers. I'm going to use a number line. Now you might be wondering, why do we need another model? Well, there's a couple reasons why I'm going to give you another model. One of the reasons I'm going to give you another model is because some people can visualize the number line model better than they can visualize the signed chip model. Another reason I'm going to give you another model is because the signed chip model only works well when you're working with integers. If you start bringing fractional parts into the numbers, you start breaking the chips all apart, and it's kind of hard to figure out how they piece back together. It's much easier to visualize along a number line. So how do we find sums along a number line? Well, the first rule is that for a new sum, you always start at 0 on the number line. When you encounter a positive number in the sum, you move that many units right along the number line. Wherever you are on the number line, you need to move that many units right from that point along the number line. When you encounter a negative number, you move the absolute value of the number units left along the number line. And unless it is a new sum, each movement begins where the last movement left off. Let's see that in action. Let's find 4 plus 5 using a number line. Since we're doing a new sum, we are going to start at 0. Since the first number in the sum is positive, we are going to move right, specifically right 4 units. Then, picking up where I left off, which is the number 4, I need to move right 5 more units. I'm moving right because 5 is a positive number. Look where I end up. I end up at the point 9. Since I ended up at the point 9, I have just illustrated that 4 plus 5 equals 9. Now I went ahead and threw some positive chips above the number line just to help you visualize the connection between the number line model and the signed chip model. Moving right 9 units is sort of like adding 9 positive chips to the counting area. How about -4 plus -5? It's a new sum, so I'm going to start at 0 again. Since -4 is negative, I'm going to move left. How far? 4 units. That's the absolute value of -4. I'm adding -5. So picking up at -4, I want to move left 5 more units. Look where I end up. I end up at -9. Since I ended up at -9, we say that -4 plus -5 equals -9. See how moving left 4 units is like adding 4 negative chips to the pot. And moving left 5 units is like adding 5 negative chips to the pot. Let's do some bilateral kind of motion. Let's go both ways. New sum, start at 0. First number in the sum, -5. Negative means go left. 5 is the magnitude of -5, so we're going to go left 5 units. Now picking up at -5, I want to add to that 8. I need to move right 8 units. Look where I end up. I end up at +3. So we say that -5 plus 8 is +3. From the number line perspective, let's go back and look at what happened. We started at 0, and the first thing we did was we went left 5 units. We followed that by going right 8 units. Well, the first 5 steps of those 8 units just put us back where we started from. This is just like negative chips and positive chips canceling to 0. In both models, the first 10 steps, in a sense, was a waste of time. We just got back where we started with. We had 3 more positive steps to make, so we ended up at +3. Let's do a couple more examples, but let's do these by hand. In this example, I'm being asked to model the sum -3/4 plus 5/4. The first thing I'm noticing about my number line is that no points are indicated, nor is any scale indicated. So I guess that's our first order of business. Since I'm going to be going both left and right along the number line, I think I'll let 0 be a point somewhere towards the middle of the number line. Now, it's kind of easy to get in the habit of automatically assigning a scale of 1 to your number lines. Call this 1, this 2, this 3, this -1, this -2, this -3. And technically, that would not be wrong in this example, because I would be able to go left 3/4 of a unit, and then picking up from there, go right 5/4 of a unit. But I don't think I get really a very good illustration of the motion using this scale for 2 reasons. One is all of the movement would be crammed into this one weeny little part of the number line. Another reason is I'd only be able to estimate where -3/4 and +5/4 are on the number line. So I think I'm going to choose a different scale. I'm going to stick with 0 being in the middle of the number line. But rather than having a scale of 1, I'm going to use a scale of 1/4. I'm going to call this point 1/4. This point is 2/4. This point is 3/4. This point is 4/4, which is just 1. Going in the negative direction, we have -1/4, -2/4, -3/4, -4/4, which is -1. If you're wondering why I didn't reduce 2/4 and -2/4, I just kind of wanted to see the pattern with the fourths. But I just didn't want to extend it just too ridiculously into writing 4/4, so I did go ahead and simplify that one. Hey, I am set up for success in modeling -3/4 plus 5/4. It's a new sum, so I'm going to start at 0, and the first thing I need to do is I need to go left 3/4 units. I think I'm going to draw my line above the number line because I can see I need to go both back and forth And it's going to be kind of hard to illustrate that with a pen if I actually draw on the number line. So the first thing I'm going to do is I'm going to start at 0, and I'm going to go left 3/4 of a unit. Now, picking up where I left off, I need to go right 5/4 of a unit. Somebody handy-dandily set up units or in a scale that worked in quarters on my number line. So if I want to go right 5 units, all I need to do is count 5 tick marks. So picking up at -3/4, I want to go 1/4, 2/4, 3/4, 4/4, 5/4 right along the number line. Notice I used my straight edge because I certainly wouldn't want to draw a line without using a straight edge. Check out where I landed. I landed at 2/4. Does this make sense? Well, let's think about how we add fractions. -3/4 plus 5/4, we have a common denominator in our sum. So all we need to do is add our numerators over our common denominator. -3 plus 5 is 2, and this is over 4. Check it out. That's where we landed on the number line. Now, since I am writing my official answer, so to speak, I am now going to go ahead and reduce this fraction to a half. Let's see one more example. Let's add -5.07 to 8.3. Again, I have no numbers or scale on my number line. So the first thing that I need to do is figure out how do I want to label the numbers and scale on my number line. Now, I'm not going to be able to label it conveniently with quarters like I did last time because I'm not working with quarters. And I think since 5.07, that's a decimal that's down to the 1/100th, the only way I'd be able to label my tick marks with labels that would allow me to let this sum end up on a tick mark is if I use 1/100th as the scale. If I use 1/100th as the scale, I'd need to go 8.3 times 100, which is 830 tick marks to the right for the first part of the motion. I don't want to go 830 tick marks to the right for the first part of the motion, so I think I'll just live with a scale of 1. I also notice that the first number in the sum is 8.3. If I make 0 the middle of the number line and I use a scale of 1, check out what happens. 1, 2, 3, 4, 5, 6. I run out of tick marks before I get to 8. So I don't think I want 0 in the middle of the number line. How about if I put 0 on the left side of the number line? Am I going to be okay then? Well, let's see. I'm sure I have plenty of room to go 8.3 units to the right now. And since I'm adding a negative number, the next motion is going to be left, but I'm not going to go back left as far as I went right. So I'm not going to get back to 0. So it looks like having 0 here is going to cover our tracks. Now, I already said I want to use a scale of 1. I think this time I'm only going to indicate the value of every other tick mark. So this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10. New sum, start at 0. Drawing a line, get out the ruler. So starting at 0, I want to go right 8.3 units. So that's farther than 8, but not quite to 8.5. So I just kind of have to make a little bit of an eyeball here that I'm past 8, but I'm not quite half past 8. So this is the point that I'm using to estimate 8.3. Now what I need to do is I need to go left 5.07 units. That's just a wee bit more than 5 units. So getting out the ruler, picking up where I left off, I need to go left 1, 2, 3, 4, 5, and just a wee bit more. And that's my stopping point. Let's figure out what the value of that point is on the number line. Let's see. I know that the positive number in the sum has the larger absolute value. Since the two numbers have opposite sign, the sign on the sum is the same as the sign on the number that has the larger absolute value. So the sum is positive. That's good. That matches our number line. We're in positive territory. What's the absolute value of the sum? It is the difference, the positive difference between the absolute values of the two numbers in the sum. So essentially, what I need to do here is I need to take 8.3. I'm kind of doing this on scratch paper, kind of metaphorical scratch paper here. I need to take 8.3 and I need to subtract from that 5.07. So let's see what we get. Let's see, we got a 3 there. We had to borrow 1 from that 3 to get that 3. So we've got 2 minus 0 there, and we have a 3 when we subtract 5 from 8. This is my scratch work. What do I write on my paper? I write that 8.3 plus negative 5.07 equals 3.23. That's the point I have on my number line there, 3.23. Now, I did something kind of sneaky there. I took this addition problem and I turned it into a subtraction problem. Candace is going to do all sorts of sneaky stuff like that in her part of the lesson, which is subtraction of signed numbers.
Now I'm going to talk about subtraction of signed numbers. Let's start by evaluating 7 minus 3, something I know we can do without using the chip model. But let's do it with the chip model just to get used to what we're going to do with subtracting. Since we have positive 7, we need to put 7 positive chips into our counting area. And then we're subtracting positive 3, so we'll need to remove 3 positive chips from our counting area. Once we do that, that leaves us with 4 positive chips in our counting area. And as we know, 7 minus 3 is equal to 4. All right, so let's make it a little bit more difficult. What if we wanted to add 7 and a negative 3? Well, again, we would start with 7 positive chips in our counting area. This time, we need to add 3 negative chips in our counting area. Once we do that, we look for our pairs of positive and negative chips, which nullify each other. And here we have 3 pairs of positive and negative chips. So we can trade those in for 0 chips. 0 is the additive identity, and when we add 0 to a number, it doesn't change the number, so we can go ahead and get rid of those 0 chips. That leaves us with 4 positive chips in our counting area. So we write for our solution 7 plus negative 3 equals 4. Well, let's make an observation here. We looked at 7 minus 3, and we got 4. We looked at 7 plus negative 3, and we also got 4. So 7 minus 3 is equal to 7 plus negative 3. Now let's evaluate negative 6 minus 2. This time we need to start with 6 negative chips in our counting area. And we need to take away 2 positive chips. The problem is I don't have any positive chips in my counting area right now. I can easily put zeros into my counting area. This doesn't change my sum or difference in this case at all. And remember, these 0 chips can always be traded for a pair of positive and negative chips. So I've got 2 0 chips. I'll trade those in for 2 pairs of positive and negative chips. Now I do have the positive chips that I need in my counting area. And in my counting area, I still have something that represents negative 6. So from negative 6, I need to subtract positive 2. So I'm going to take those 2 positive chips out of my counting area. When I do that, that leaves 8 negative chips in my counting area. So I can say that negative 6 minus 2 is equal to negative 8. Now let's try evaluating negative 6 plus negative 2. This time I just put 6 negative chips in my counting area, and I add 2 more negative chips in my counting area. This gives me 8 negative chips in my counting area. So negative 6 plus negative 2 is equal to negative 8. Well, let's make another observation here. We looked at negative 6 minus 2, and we got negative 8. We also looked at negative 6 plus negative 2, and got negative 8. So negative 6 minus 2 is equal to negative 6 plus negative 2. Negative 6 plus the opposite of 2. So what's the pattern? Thinking to our last 4 examples, we saw that 7 minus 3 was equal to 7 plus the opposite of 3, or 7 plus negative 3. We saw that negative 6 minus 2 is equal to negative 6 plus the opposite 2. So it looks like when we're subtracting a positive number, we could get the same result by adding the opposite of that number. That is to say, if A is any number, and if B is any positive number, then A minus B is equal to A plus the opposite of B. Now you might be wondering at this point, does this work with negative numbers also? What if B were a negative number? Well, let's try. Let's evaluate 4 minus negative 3 using our chip model. This time, I need to start with 4 positive chips in my counting area. I'm going to need to subtract 3 negative chips. I don't have any negative chips in my counting area right now, so I need to do something to get 3 negative chips into my counting area. Of course, I can put zeros in my counting area and not change the value. This still represents positive 4. And we can take these zeros and replace them with pairs of positive and negative chips. 1 positive chip and 1 negative chip nullify one another. So we have 3 zero chips. We'll replace those with 3 pairs of positive and negative chips. So what I have in my counting area still represents positive 4. Now I need to do the subtraction. I need to take out 3 negative chips. So I'm going to remove those 3 negative chips from my counting area. And I'm left with 7 positive chips. So I can write 4 minus negative 3 is equal to 7, the 7 positive chips in my counting area. Well, let's make an observation here. We just found that 4 minus negative 3 is equal to positive 7. Obviously, 4 plus positive 3 is also equal to positive 7. So 4 minus negative 3 is the same thing as 4 plus 3. If A is a real number and B is any real number, this time we're talking about B being positive or negative, A minus B equals A plus the opposite of B. Well, let's use this rule to compute a couple of differences. The first difference here we have is 32 minus 68. So I start out writing my problem, 32 minus 68. And I can rewrite this as an addition problem. So I can rewrite this as 32 plus the opposite of 68. The opposite of 68 is negative 68. So now I'm adding 2 signed numbers that have opposite signs. I have a positive 32 and a negative 68. So I need to stop and think about what is the sign of the sum going to be. I look for the number with the largest absolute value, in this case, negative 68, since 68 is larger than 32. Negative 68 has the larger absolute value. So when I add these 2 numbers, my result will be negative. Now I need to subtract the absolute values. So I need to subtract 32 from 68. 68 minus 32 is 36. So my result is negative 36. 32 minus 68 equals negative 36. Let's try negative 3 minus negative 5. The first thing I'm going to do again is rewrite this as an addition problem. So to rewrite this as an addition problem, I have negative 3. To that, I'm going to add the opposite of negative 5. The opposite of negative 5 is positive 5. Now I'm adding 2 numbers which have opposite signs. This time, the positive number has the larger absolute value. 5 has a larger absolute value than negative 3. So my answer is going to be positive. And I just need to subtract the absolute values. 5 minus 3 is 2. So negative 3 minus negative 5 is positive 2. Let's try a couple more. 8/3 minus negative 4/3. First, I'm going to rewrite this as an addition problem. 8/3 plus the opposite of negative 4/3. The opposite of negative 4/3 is positive 4/3. I have two fractions with common denominators, so I just need to add the numerators and write that over the common denominator of 3. 8 plus 4 is 12, so I have 12/3. 3 goes into 12 4 times, so this reduces to 4. Now let's try negative 3.8 minus 7.3. Negative 3.8 minus 7.3 can be rewritten as an addition problem as negative 3.8 plus the opposite of 7.3, which is negative 7.3. So I'm adding two numbers that have the same sign. Both of these are negative numbers. So I know my result is going to be negative, and I just need to add their absolute values. So 3.8 plus 7.3 is 11.1, which tells us negative 3.8 minus 7.3 is negative 11.1. Now let's do an example using a number line. Here we want to find pi minus 4. Notice here that my number line doesn't have any scale, so I'm going to need to start by deciding how to scale my number line. I need to remember that pi is about 3.14. Pi minus 4 is the same as pi plus the opposite of 4, which is negative 4. So I know when I set up my number line, I'm going to need to move right pi units, which is about 3.14 units. And then the negative 4 tells me I'm going to pick up from pi and move left 4 units. So I think I'm going to have plenty of space if I put 0 about at the middle of the number line. And I'm just going to use 1 for my scale, since I need to move a little more than 3 units right, and then from there move 4 units to the left. So 1, 2, 3, 4, 5, 6. And at the negative side, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. So I want to move pi units to the right, remembering that we always start a new sum at 0. So I'm going to start at 0, take out my ruler, and move a little more than 3 units to the right on my number line. So a little more than 3 units to the right. So this is representing pi on my number line, about 3.14. Now I want to pick up where I left off and move 4 units to the left. So I put my ruler back, and picking up where I left off, move left 1, 2, 3, 4 units. And I end up at this point a little bit to the right of negative 1. My result is between negative 1 and 0, but a little bit to the right of negative 1. This represents pi minus 4. Now, if you're not very used to working with pi and you want some kind of an idea of what this number is other than something a little bit to the right of 1, we can approximate this. We use our approximately equal to symbol and say, okay, pi is approximately 3.14. To that, we're adding negative 4. We're adding two numbers that have opposite signs. So we look for the number with the larger absolute value. Negative 4 has a larger absolute value than pi, or our approximation, 3.14. So I know my result is going to be negative, and I need to subtract the absolute values. That is, I need to subtract, in this case, 3.14, the number with the smaller absolute value, from 4, the number with the larger absolute value. And 4 minus 3.14 is 0.86. So we can say that pi minus 4 is approximately negative 0.86. And that would be a number a little bit to the right of negative 1 on our number line. Let's look at another example with a number line. Here I want to find 3 pi minus pi. I'm going to start by rewriting this as an addition problem. 3 pi minus pi can also be written as 3 pi plus the opposite of pi, that is plus negative pi. Again, I need to decide what kind of scale to use for my number line. Looking at my sum over here, I'm starting with 3 pi. I need to move 3 pi units to the right. Well, pi is about 3.14, so if I multiply something close to 3.14 by 3, I'm going to get a number larger than 9. So I'm going to need to start by moving more than 9 units to the right on my number line. Then I'm going to come back about pi units. The negative pi tells me to move leftward, so I pick up from where I left off at 3 pi and move to the left just pi units. So if I use 1 for my scale on my number line, I want to make sure that I have enough space on here to be able to move a little more than 9 units to the right. So I'm going to put 0 to the far left on my number line. Let's say this tick mark represents 0. Then the first tick mark's representing 1, the second tick mark's representing 2, since I'm going by ones, 3, 4, 5, 6, 7, 8, 9, 10, and I just have 1 tick mark over here on the left of 0, which is negative 1. So I want to start my sum, as always, at 0, and I want to move 3 pi units to the right, so a little more than 9 units to the right. So starting at 0, I want to move a little more than 9 units to the right on my number line. So this would represent the point 3 pi on my number line. Now I want to pick up where I left off and move pi units to the left on my number line. Pi is about 3.14, so I want to move a little more than 3 units to the left on my number line. So picking up where I left off, left 1, 2, 3, and a little bit more. So this point on my number line would represent 3 pi minus pi. And I can see that the number is in between 6 and 7, a little bit closer to 6 than 7 though. Again, that might not mean a whole lot to me, so I might want to go through and do my addition here. 3 pi plus negative pi, or we can think of this as subtraction if that's easier for you. 3 pi, take away 1 pi, leaves us with 2 pi. 3 pi minus pi is 2 pi. Well, now you might be saying, that still doesn't make a lot of sense to me. I don't work with pi a lot. I don't know what 2 times pi is. So if we want to approximate this, we can go back to our approximation for pi and say, okay, this is approximately 2 times 3.14. And 2 times 3.14 is 6.28. For my last example, I want to look at the same problem again, 3 pi minus pi. This time I'm going to use a little bit different scale on my axes. Sometimes later on in mathematics, if you take a class called trigonometry, you'll see problems where you often use a scale involving pi. So on this number line, instead of going by ones as I did when I did this problem on the previous slide, I'm going to use a scale involving pi. So I'm still going to put 0 over here to the left on my number line. And I'm going to make every tick mark represent 1/2 pi. So 1/2 pi, the second tick mark would represent pi. The fourth tick mark would represent 2 pi. The sixth, 3 pi. The eighth, 4 pi. And so on. And then to the left of 0, the first tick mark is negative 1/2 pi. The second tick mark is negative pi. Let's rewrite this as an addition problem again. So 3 pi minus pi is the same as 3 pi plus the opposite of pi, or plus negative pi. So using my new scale on my number line, I want to move 3 pi units to the right of 0. So starting at 0, I want to move 3 pi units to the right. And now I can see that I end up at 3 pi on my number line. Then the negative pi tells me to move pi units to the left on my number line. So picking up where I left off, pi units to the left puts me at 2 pi. Same result we got before, 3 pi minus pi, or 3 pi plus the opposite of pi, is 2 pi. Now I want to turn it over to Anne, who's going to talk about multiplication and division of real numbers.